All right, let's boot this up. Welcome to this Architecture First Explainer. Today we're initializing our master schematic of the May 2026 open-source AI ecosystem, and we are looking at this shift purely from the metal up. We're talking raw system blueprints, kernel-level optimizations, and the specific terminal logic that is literally defining the autonomous enterprise era.
Okay, look at this terminal log, because the paradigm has violently shifted. We're just no longer living in an era defined by brute force parameter hoarding inside massive hyperscale data centers. That's over. The real engineering bottleneck has moved. It's not about raw model capability anymore. It's all about localized deployment, orchestration, and somehow squeezing massive capability right down into edge efficiency.
So here is our raw system blueprint for today. We're compiling 6 core layers: the edge deployment paradigm, architecture of sparse MoA models, hardware constraints with W4A4 quantization, kernel-level inference engines, execution multi-agent frameworks, and finally, PEFT weight space calibration.
Let's initialize Layer 1, the edge deployment paradigm.
Developers aren't just blindly downloading monolithic models anymore. Instead, they're deploying localized, highly efficient daemons. Take the Mini CPM51B, for example. It is a dense 1 billion parameter transformer, but it comes with a massive 131,000 token context window. And it's establishing a totally new state-of-the-art for its class, hitting a 42.57 average across reasoning and agentic benchmarks. But you know what the real game changer is here? It's the architecture. It integrates a built-in think chat template, which actually lets developers toggle hybrid reasoning via an enable thinking flag. So you can seamlessly switch between snappy assistant responses and deliberate chain of thought traces completely on device.
Moving up the stack to Layer 2, architecture and sparse MoE models.
This number brilliantly illustrates the MoE magic. Just 3 billion. That's the exact number of active parameters Alibaba's Qwen 3.635B 83B is using per token. Now, the model has 35 billion total parameters sitting right there on the disk, which gives it massive representational capacity and routing intelligence. But during inference, it gates its feed-forward networks so aggressively that computationally it behaves like a tiny 3 billion parameter model. And this extreme sparsity ratio is incredible because it means you can run complex repository-level coding workflows with unprecedented token per second throughput right on localized hardware.
These active parameter ceilings are everything. They absolutely dictate our VRAM bandwidth survival across all frontier models. You've got Qwen 3.6 running incredibly lean at 3B active. Then you scale up to Cohere's Command A+, which is a massive 218 billion parameter generalist, but it activates 25B per token. And then look at Shipu AI's GLM5. It was trained entirely on Huawei Ascend NPUs and operates at 44B active parameters. Ultimately, your specific hardware architecture fundamentally dictates which of these beasts you can actually deploy.
Dropping into Layer 3, hardware constraints and W4A4 quantization.
Let's ping the underlying syntax of Command A+ right out of its Hugging Face repository. This is a gloriously geeky look at its recipe.yaml for W4A4, meaning 4-bit weight and 4-bit activation quantization. Now, historically, 4-bit activations would just catastrophically degrade reasoning capabilities because outlier values would clip. But Cohere totally solved this. They're using a highly granular group size of 16 mapped to an 8-bit float scale data type. This strict bounding of the quantization error, paired with dynamic local symmetric float activations, basically stops catastrophic KV cache bloat on their massive 128K context window. Because of this exact recipe, you can run an enterprise-grade model on just 2 H100s or a single B200 rather than needing an entire 8x H100 cluster. Okay, Layer 4, kernel-level inference engines. Listen, brand loyalty is dead. Your inference engine selection in May 2026 is strictly dictated by concurrency and workload geometry. Full stop. If you're chasing max quality on a single workstation with an RTX 5090, Llama.cpp or XLlama v3 is your backend. Period. But if you need to serve 20 concurrent enterprise users, you're shifting immediately to VLLM on a Pro 6000. It's a highly segmented, purpose-built ecosystem now, and deploying the wrong engine for your specific workload geometry will completely bottleneck your hardware.
Now, if you are fighting that context bottleneck on local GPUs, this specific terminal command syntax is literally your lifeline. To run massive MoE models on consumer hardware, llama.cpp formalized the NCMoE flag. So, by typing NCMoE 25, you're pinning the most frequently accessed expert layers directly into GPU VRAM and offloading the rest to your system RAM. It totally bypasses that nasty PCIe bottlenecking. Contrast this with Apple Silicon's unified memory architecture, where you just use n_GPU layers equals to -1 to effortlessly offload the entire transformer stack to the Metal API. It is a completely different approach to memory topology.
But hey, bleeding-edge kernel fusions carry massive friction. Just look at this volatile VLLM release cycle timeline from May. Version 0.20.0 drops, bringing incredible features like Eagle 3 speculative decoding. Awesome. Then 0.20.1 stabilizes DeepSeek workloads. Great. But then v0.21.0 shipped, and enterprise production logs absolutely lit up because it entirely broke the multi-token prediction rate for Qwen 3.627b. It dropped prediction efficiency to literally 0%. This kind of volatility forced massive enterprise deployment rollbacks, which is a stark reminder. You absolutely must rigorously benchmark your runtime engines before upgrading any production environments.
Let's clear the cache and elevate to Layer 5, execution and multi-agent frameworks. Frameworks like LangChain 1.0 Alpha and Hermes v0.14.0, they aren't your basic chat wrappers anymore, not even close. They are fully asynchronous root access daemons. Hermes operates bare metal right on your file system. Through its local SQLite engine, it's maintaining persistent memory and identity across all your sessions. It even features cross-session prompt caching and language server protocol diagnostics, which is wild because it allows the agent to self-correct code syntax before it ever pollutes the LLM's context window.
Let's step through and see how this builds into true system optimization with Microsoft's SkillOpt framework. We're officially moving away from trial-and-error prompt engineering and getting into pure algorithmic text space optimization. Here's the cycle. A frozen target model does a rollout. Then, a more capable optimizer analyzes the trajectory in a reflection step and proposes edits to the markdown skill file. Next, a textual learning rate bounds exactly how many characters can be changed, so the file doesn't get destroyed. And finally, validation gating ensures those edits only commit if they actually boost benchmark scores. It is a zero-overhead algorithmic optimizer running purely in Markdown text space, and it boosted accuracy on real enterprise tasks from 41% to 80% without touching a single model weight. Mind-blowing.
And finally, Layer 6, PEFT and weight space calibration.
So, catastrophic forgetting. We all hate it. But the pre-tune architecture permanently resolves this knowledge inconsistency, which, is when a model starts hallucinating because fine-tuning new skills forced it to override its pre-trained facts. Pre-tune solves this by freezing a knowledge LoRa, a low-rank adaptation right beneath an active skill LoRa. By cleanly disentangling what the model knows from what the model does, it drives hallucination rates down to an absolutely incredible 0.6%.
And deploying all of this is easier than ever because MLOps is now fully industrialized. Llama Factory just integrated the ultra-fast UV resolver along with FP8 training. Unsloth has baked right into the PyTorch ecosystem, delivering kernels that are 2 to 5 times faster for RL tuning directly on local UIs. And we're even seeing zero-shot video and voice identity preservation natively integrated into comfy UI workflows thanks to LTX 2.3 ID LoRa. The kind of high-end, multimodal fine-tuning that used to demand a massive data center is now officially industrialized for the local platform engineer.
As we terminate this explainer session, I want to leave you with a core system diagnostic to evaluate your own stack architecture. Look at your setup. Are you just passively renting API endpoints totally subject to the whims and pricing of hyperscalers? Or are you actively compiling the autonomous enterprise era on your own local silicon? The tools, the hypersparse architectures, the raw kernel optimizations, they're all just sitting right there in open source repositories waiting to be orchestrated. The metal is ready. The real question is, are you? Keep optimizing your stacks, and I'll see you in the next explainer.